Hey guys, so today we're going to be looking at question 7153 from the thermo textbook. We're just to start by reading through the problem. So steam expands in a turbine steadily at a rate of 40,000 kilograms per hour, entering at 8 megapascals and 500 degrees Celsius, leaving at 40 kilopascals as a saturated vapor. If the power generated by the turbine is 8.2 megawatts, determine the rate of entropy generation for this process and assume that the surrounding medium is 25 degrees Celsius. So coming down to our assumptions below our little diagram, we're going to see that we're assuming steady flow, meaning that our m dot 1 is equal to our m dot 2 is equal to our 40,000 kilograms per hour. And to make the math a little bit easier for us later in the problem, we're going to convert this to kilograms per second. And after this, we're going to realize that the mass flow for the whole system is equal to 11.11 kilograms per second. Additionally, we're going to note that at steady flow, we have our delta E dot for the entire system is going to also equal 0. Additionally, we're going to neglect kinetic energy and potential energy. We're going to convert our power out from 8.2 megawatts to 8,200 kilowatts. We're going to note that our inlet pressure is 8 megapascals or 8,000 kilopascals. Our T1 is 500 degrees Celsius or 773 Kelvin. Our P2 is 40 kilopascals and it's at a saturated vapor. And our ambient outside temperature is 25 degrees Celsius or 298 Kelvin. Now, nowhere in the process is this defined as an adiabatic turbine. So there's going to be some entropy generated to heat transfer. And we're going to assume that this heat transfers out of the system because the steam enters at a very high temperature and pressure and leaves at a significantly less pressure. So noting that the problem statement is asking us to determine the rate of entropy generation, we're going to start off with entropy balance. Now, from our notes, we see that our S.1 value, or in, minus our S.2 value, plus our S.gen is equal to our delta S dot for the system. We're also going to note that for steady flow devices, when we take a derivative of entropy across the control volume with respect to time, it's going to equal 0. So our delta S for the system is also 0. Now, additionally, we have to consider, since this is steady flow, we have to consider entropy due to mass flow as well as heat transfer. So when we write this next equation out, we're going to break our S1 and S2 terms into mass flow as well as heat transfer entropy generation, or entropy. So we have our m dot specific enthalpy or entropy at state 1 minus our m dot specific entropy at state 2 minus our q dot value, and we're going to note that it's q out, and since it's getting rejected to the outside ambient temperature, we're going to have that over T naught. And then finally, we have our S dot gen term, which we're going to keep as a big S, and that all equals 0. Finally, reordering this equation for our desired S gen term, we're going to note that S gen equals our m dot times entropy at state 2 minus state 1 plus our q dot out over T naught. Now, noting that we don't have many of these values to work with, we're going to actually start over here to solve our q dot out. And we're going to use this using energy balance. Now, knowing that our E dot 1 is equal to our E dot 2 from our problem solution and assumptions from steady flow, we're going to break this down a little bit further in saying that our m dot 1 times our enthalpy, our specific enthalpy at state 1, is equal to our power out plus our heat out plus our mass flow times specific enthalpy at state 2. When we rearrange this for Q dot out, we get that Q dot out is equal to the mass flow times specific enthalpy at state 1 minus state 2 minus our power out. Now, knowing that we don't have any enthalpy or entropy values to work with, we're going to start looking at our steam tables to get this tabulated data. So noting that our inlets are our inlet conditions are 8 megapascals and 500 degrees Celsius. We see that that is too high of a pressure and too hot to be in our saturated liquid vapor mixture table. So we're going to have to start in table A6 to find our first values. And when we look at our 8 MPa and 500 degrees Celsius, we see that our specific entropy at state 1, or specific enthalpy at state 1, is equal to 3,399.5 kilojoules per kilogram. Now, before we move on to the next one, we note that we have to eventually get our specific entropies for the same states when we go back to entropy balance. So we're just going to grab that right now and note that the specific entropy at state 1 is equal to 6.7266 kilojoules per kilogram Kelvin. Now, realizing that our state 2 is a significantly lower pressure and it's a saturated vapor, we're going to have to look in our table A5, realizing that it's no longer a superheated vapor. Yet, it is not a liquid vapor mix yet, so we're just going to be considering our values under the saturated vapor columns for specific entropy and enthalpy. So with this said, we note that our specific enthalpy at state 2 is equal to 2,636.1 kilojoules per kilogram. And our specific entropy at state 2 is equal to 7.6691 kilojoules per kilogram Kelvin. So with this data, we can now solve for both our Q dot and then go back to our entropy balance. So with this said, we get that our Q dot out is equal to our 11.11 kilograms per second times our enthalpy difference of 3,399.5 minus 2,636.1 kilojoules per kilogram. And then we're going to minus our 8,200 kilowatts of power. Noting that our kilograms cancel out and we're left with kilojoules per second and kilowatts, those two units are equal, so that's a good sign. And we get that our final Q dot out is equal to 281.374 kilowatts. Now with that said, we're going to move back to our entropy balance over here and bring this down a little bit so we got some room. We see that our S dot gen is equal to our M dot of 11.11 kilograms per second. Between the difference of our entropies, which we have 7.6691 minus our 6.7266, and those are both in kilojoules per kilogram Kelvin. And then we add our recently calculated heat and entropy, or heat transfer, or entropy due to heat transfer, which is our 281.374 kilowatts over our ambient outside temperature of 298 Kelvin. So again, noting that our kilograms cancel out and we're left with kilowatts per Kelvin, we see that our units once again match up, which is good. And we breaking down these two terms, we find that the first one is 10.4712 kilowatts per Kelvin, plus the second term of 0.9442 kilowatts per Kelvin. And finally, by adding these two values together, we get that our S dot gen is equal to 11 11.415 kilowatts per Kelvin. Now, before we leave today, we're going to note that if we come back up to the beginning and we see the answer that's provided by the book, see that the answer is 11.4 kilowatts per Kelvin, and our answer is 11.415 kilowatts per Kelvin. So we're pretty close on that. With that said, thank you for listening. I hope you learned something.